Welcome to FYI, the For-Your Innovation podcast. This show offers an intellectual discussion on technologically enabled disruption, because investing in innovation starts with understanding it. To learn more, visit arc-invest.com.
ARC Invest is a registered investment advisor focused on investing in disruptive innovation. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. It does not constitute, either explicitly or implicitly, any provision of services or products by ARC. All statements made regarding companies or securities are strictly beliefs and points of view held by ARC or podcast guests and are not endorsements or recommendations by ARC to buy, sell, or hold any security. Clients of ARC Investment Management may maintain positions in the securities discussed in this podcast.
Hi, welcome to FYI, the For Your Innovation podcast. I'm Brett Winton. I direct research for ARC Invest. With me today, I have Tasha Keeney, who is our analyst on autonomous vehicles, and we're going to interview Alex Kendall, who is the CEO of Wayve.ai. Tasha, why are we interested in autonomous vehicles in general?
Well, the research that we've done at ARC shows that an autonomous taxi could price to the consumer at scale at about 25 cents per mile. This will be very cheap, which is what we think will drive adoption. It'll be less than half the cost of driving your personal car and a tenth of the cost of a taxi today. So this will drive wide-scale adoption of the technology and could cause people to stop using their personal cars and get in autonomous taxis.
And so remind me, how big a market does that potentially unlock?
So we think that autonomous taxi platforms globally today should be worth about $2 trillion. That's if you look at the 10-year forward net present value of the cash flows that we expect off these systems. We expect them to be very profitable with software-like margins. So this will be a much higher margin business than, say, the auto industry today. So in fact, we think that in the next 10 years, autonomous taxi platforms could be worth more than today's energy sector. So this will be a huge market opportunity.
And when you talk about taxi platforms, are you talking about the Fords or the Toyotas? Like, who are those companies going to be?
We think the leaders in this industry are going to be the companies that actually develop the autonomous technology themselves. So right now we're looking at Tesla, Waymo, Google's project is also developing their own technology, companies like Baidu in China or AutoX. These are the companies that are actually developing the technology platforms themselves. So it won't necessarily be, say, the ride-hailing companies or the traditional auto players that we see today as the winners of this market.
Or it could be Wayve.ai, I suppose, right?
Yes, of course. Yeah, Wayve.ai.
And so then what makes Wayve.ai interesting?
Yeah, so Wayve doesn't use HD maps for autonomous driving. And a lot of people do. So Waymo does, for instance. A lot of the technology startups use LiDAR and HD maps to run their platforms. But Wayve uses end-to-end deep learning, which is what makes it unique.
Yeah, it's kind of like, autonomous systems have existed for a long time. I could put a train on a set of tracks and run it without a driver. I've been able to do that for a long time. It seems like the real challenge in this space is how do you balance your ability to get product to market against your ability to generalize a solution that will scale. And it seems as if, Alex and Wayve have an interesting approach to that. So that's the conversation we're looking forward to having with them.
Exactly. So let's get to Alex. Alex, thanks so much for joining us.
Delighted to be here.
I'd first like to start off by asking you, why did you start Wayve and what is Wayve's mission?
It's an interesting one. If you think back to 2017, this was when we'd seen many years of deep learning starting to completely revolutionize so many complex decision-making problems in computer vision, speech, natural language. And a lot of the research that we were doing at the University of Cambridge really uncovered the ability for us to do this in real-world robotics. And this is something that at the time and still today, the robotics industry is very skeptical across, but is firmly how I think we're going to be able to scale this technology. So our mission is to build really scalable, adaptable robotics for learning algorithms for self-driving cars. And if you think about what's required to scale mobility to society, it's really about being able to adapt very efficiently. Take humans, for example. You can go on holiday to a new destination, pick up a rental car, and learn very quickly to drive in that environment. We see a future where robots can do the same thing. And when you think about domain adaptation, it's to new geographies, new vehicle types, new mobility use cases. It's not just about the race to getting self-driving cars deployed, but how can we continuously add value to society? Even recently, so we're based in London, and in the coronavirus pandemic, we've had our footpaths extended by a couple of meters to aid social distancing. So the world's continuously changing. We've seen different mobility applications rise in the last couple of years, and we need to be able to very quickly learn and adapt to these things. And that's what we're pioneering with machine learning.
Great. So that brings me to the next question. I'd love you to explain to our listeners why your approach is different to autonomous driving and why it's so adaptable.
We've made the bold step about committing to going to a full end-to-end learning approach. This means that we use machine learning to optimize driving algorithm end-to-end, right from the input to the output, where the input for our self-driving car is camera sensor data and the output is a motion plan for the vehicle. And by learning end-to-end, it enables us to achieve a level of efficiency that you can't attain with a traditional rules or LiDAR or HD map-based approach that many of the incumbents use. And by learning end-to-end, we can enable a very lean team of elite deep learning engineers to build a system and really scale to the complexity of driving through learning. If you think about the environments that we drive through in London, they're very complex. It's very hard to hand structure them with lane layouts because these medieval cities don't have clear lanes. There's very complex driving structure that needs to be learned in a high dimensional representation. So that's what we can do with machine learning. And we go a step beyond some of the other approaches that teams like Tesla do with machine learning for just perception, but also learn control. This is the critical thing. There's what we've seen enable breakthroughs in artificial intelligence, like Google DeepMind's AlphaGo, the system that was able to use deep reinforcement learning to beat the world champion at the game of Go, one of the hardest board games. This was only possible, or only shown to be possible, through end-to-end learning. And we see the same technology being able to scale the complexities of urban driving.
So the advantages to this approach seem clear. What would you say have you found are potential limitations or parts that might be more difficult with your approach?
If you think about the key breakthroughs that have enabled this to be possible, it's only in the last couple of years that we've been able to train systems that have been data efficient enough and robust enough to actually put in the real world and not just exist in simulation. So this largely ruled it out for self-driving teams that got started, certainly earlier in the 2010 decade. But some of the challenges that we face with this approach, I think the first one that we're quite open to admit is around interpretability. Typically, deep learning systems, although they're the most robust, generalizable systems that humanity knows how to build today, they tend to be quite high dimensional and hard to interpret. But having said that, that's rapidly changing. It's no longer interesting for PhD students to simply chase benchmarks. ImageNet's been largely solved. We've got amazing NLP systems today. Today, the real research challenge in deep learning is how do we make these systems transparent, trustworthy, interpretable, and to really understand the causality in their decision making. And so I think this is something that we're making great progress in. But for us, it's about being able to unlock and solve the problem of data efficiency, understanding the distribution of data we can train from, and making sure it solves a problem robustly.
Why does interpretability actually matter at a root level? Is that more for external parties to be able to say, like, oh, this is why it did this? Or is that for, in terms of your own state of development, to say, oh, we understand exactly what's being miscoded here to do relabeling or whatever remediation steps you need to do?
Yeah, look, I think that's a bit of an open question. Certainly, it's essential for us as engineers to be able to develop the system. It's unclear what the regulatory stance will be. It's most probable that we'll need to provide, and we should be providing, some interpretability for why a decision was made. But if you think about in a human car accident situation, humans aren't often able to provide their own interpretability for why a decision is made. They might provide an explanation, but is it a causal reasoning explanation? No, I don't think so. So I think we can do better than humans there, but how far we go is an ongoing discussion. And then on the consumer side, it's unclear how much customers will drive this. If you think about aircraft, an airline passenger doesn't have strong demand for interpretability of why and how the aircraft is flying. They just experience the transport service. And so I'm still unsure what the consumer demand will be for interpretability. We've seen systems like the autopilot provide a number of computer vision outputs on their display. There are a number of erroneous outputs, but consumers seem to prefer it, even though it's not always 100% accurate. So that's something that we're still actively exploring and have an open mind to.
It seems like intrinsically the approach of imitation learning is very attractive, right? It's kind of like the way humans learn. And so you can read academic papers on it, and then implementation-wise, I'm sure it's challenging. Do you even go so far as you're not even labeling like street signs or anything? The system just has to figure out that a stop sign is a stop sign? Is that accurate?
One of the things that blew me away was when we trained a system with imitation learning purely from images to driving commands. And we saw it for the first time slow down at giveways and stop for traffic lights without ever having told it what a traffic light was. And when we actually, some of the interpretability systems that were built are systems like attention and saliency. And when we looked at what the model was attentive to in the input image, it highlighted the traffic sign. And that was amazing that the model was able to discern the pattern in the data that was most strong in the driving behavior was things like a traffic light to be able to make that decision. So that blew me away. I think that was back in early 2019. But we use a number of learning signals from supervised to unsupervised or self-supervised to reinforcement learning. And one of the most important things for us to build up was an understanding of how to mix these together in a multitask fashion. So we can use expert policy data. We have chauffeur drivers driving our vehicles, constantly collecting expert driving data. We can learn to do imitation learning with that, and that's supervised. We also have algorithms driving on public roads, and that's on policy testing, essentially putting them through a driving school, and we have safety drivers intervening and teaching them, and that's reinforcement learning. We also have some supervised learning on semantic segmentation, and then self-supervised learning on geometric understanding, depth, how the world is laid out. And putting all these different learning signals together, going back to what I said about trying to make the most data-efficient learning system, that's one of the biggest challenges that we're faced and what we spend a lot of time on.
I had another question on labeling. I know that you use manual labeling now for things like intent. One, do you consider labeling a bottleneck? And is there a path to reducing the reliance on human labeling?
We've only labeled two things to date, and that's the first one is semantic segmentation, which gives us a holistic scene understanding view in the image space. And then secondly is on traffic light detection. And we're actively pursuing methods to reduce and divest for that because it, like you say, it doesn't scale. And it also requires a human-imposed view on the data. You have to enumerate the classes, and there might be edge cases outside that. We much prefer moving towards open set or unknown understanding through self-supervision. And look, I think we can get there. Right now, we've spent in the order of £100,000 on labeling. So it's a very small part of our budget. And the predominant factor of learning is self-supervision. You mentioned on prediction and intent prediction. That's actually something we do entirely with self-supervision. What you can think about doing is, it's a very challenging problem because given a state of the world of the vehicle, we only get to see one possible future. But of course, there are many possible futures that could occur. You can debate whether the future is deterministic or not. But given the sensing capabilities that we have, there are many things that could happen. And what we do is we can look at what actually happens in the world, and we can use that as a label to train our system to do prediction. And so we don't actually have to human label intent. We can look at what does occur, but then apply a probabilistic machine learning to actually understand the uncertainty around the distribution of future prediction and intent. And that's something that needs to scale with self-supervision because you just need so much data to be able to learn that complex multi-agent understanding.
Got it.
Are you data constrained? What is the bottleneck of development for you, or the critical path? If I could give you 10x as much data, is that what you need? Do you need 10x as much compute? Do you need like a bigger deep learning model? Is it like a better understanding of what modules you need to train? Give us a sense of where your friction points lie.
Yeah. It's no longer compute. We just announced a really exciting partnership with Microsoft Azure, which is really letting us scale our learning through this large connected vehicle fleet we have, bringing this data into the cloud to create this fleet learning loop and drive our compute. That's fantastic. We've got an incredible team of deep learning engineers, and I'm confident the rate of innovation we're seeing there is going to address the problem. I would highlight data as being a really important problem for us to solve and a big bottleneck. But in particular, it's not the quantity of data, it's the quality and the distribution of data. Getting the right training data of edge cases. And if you think about, when you try and teach a human, you want to provide them with stuff on the learning boundary, not examples that are too easy or too hard that they get confused. But you want to find the right level of data. And that changes over time as your model gets better. And we need to provide the right learning curriculum for our model. And getting the source of that data is something that we've thought a lot about.
It's almost like you don't need quantity of data. You need the ability to call data in a certain domain on demand, as in stop signs. You're working on stop signs or intersections, roundabouts. And so kind of you need some like large however you're going to get it, you need to be able to like get the thing that's the problem you're working on at that time. Is that the right way to think about it?
Absolutely. It's about identification of that data. And you do need a large data source to be able to tap from, because statistically speaking, these scenarios are going to occur very rarely. So being able to have that source, but then know how to select the subset of that data is the core IP.
Do you have a sense for, so I have like a rule of thumb that I just made up that I have no idea if it's true, but it's basically as you get every additional 9 of accuracy, so like imagine if deep learning is delivering accuracy to some 9's precision or autonomous driving, as you get to each additional 9, your error rate, however you define it, is occurring at 1/10 the rate. But I also think the number of edge cases increases by an order of magnitude. So it's almost like you need 100x more data for each additional 9. Does that sound intrinsically right or wrong? Or do you have any sense what it looks like as you try to proceed down the path to get better?
Yeah, I'd agree with that. And that's why you need to do this with machine learning. If you're dealing with a 2 order of magnitude increase in complexity with each 9, and we know, for example, that what we need to get to for human performance is 5 nines. Humans can drive through a traffic light with 99.999, so 5 9% of the time without having an accident causing injury. So that's the kind of level we need to get to. And if you're going through a 100x increase in complexity with each 9, the challenge you're going to face if you're doing a rules-based system is that you're just going to be exploding with the amount of autonomy triage engineers you need to create these rules and make sure they don't interfere with each other. It blows my mind. The nice thing about machine learning is the more data we get, we just re-optimize the model and it excels rather than buckles with increasing amounts of data and complexity. It's fantastic. And so with the right data source and the right compute and learning loop, this is the future that I think we can build. I'd agree with that rule of thumb though.
How do you internally measure kind of your rate of progress? Like you say, the innovation rate is happening well. Like what is the thing that you're looking at to know, this month we're better than last month?
Yeah. Hey, we just wrote a blog series on this if you want to read it on our website, Wayve.ai/blog. But essentially, I think having the right metric we know throughout business that if you know the right metric to optimize, then that's the first step to a succeeding team. And we've seen this in machine learning, right? Like the ImageNet benchmark that really drove modern deep learning through 2010 to 15 gave us things like residual connections, batch normalization, a bunch of deep learning technologies that have made what we're doing today possible. The problem with driving is that we don't have a static trained test set, right? Every time we go out into the environment, the world changes. And so in order to really accurately measure this, we need to come up with a new testing paradigm. I think what the industry does right now, most companies will typically have a fixed route that they do every day, and then try and measure the overall intervention rate on that route or something like this. I think that's broken because it doesn't encourage scalability, it doesn't encourage diversity, and you can't really compare apples with oranges. What we've built is a system that lets us compare self-driving system A driving in location X with self-driving system B driving in location Y. And this is really powerful because it lets us compare ideas across domains. And what we do is we have a very efficient way to label every experience we have with where it exists in our operational driving domain, within what weather it is, what scenario type it is, and what the traffic is like around it. And so once we can identify exactly where that experience exists in, if we can then get enough experience in that specific bucket, then we can compare performance. So let's say we have one model that's testing driving through a roundabout in the rain with a cyclist beside us. If we can identify it's doing that, then we can compare models on level terms. And we look at metrics on a per scenario basis. This is what we use to measure and drive our performance up.
One of the things that we've been fascinated by is kind of the industry dynamics that led traditional players as well as Waymo and Tesla to say, oh, we are this many years away. And even Waymo said they were going to commercialize I think they were 3 months out from when they were supposedly going to commercialize when they said, yes, we're going to do it. And they didn't practically commercialize. They still are, maybe now they are practically commercializing 5x longer than that 3-month window that they thought. What do you think is leading people astray? What's going on there?
I mean, there's so many factors there. It becomes very hard to forecast when you have a logarithmic curve or something that has such few data points. One of the things that's fascinated me with Waymo's recent transparency about their safety report is just how capital intensive their safety validation has been. And I think there's also maybe political and other factors at play around, do you have the capital to afford to keep running in pilot mode? Are you forced to move to the stage? What is the risk around it, being first mover and all these kind of things? And I think those factors have become larger than the safety case. I suspect the safety case has been there for Waymo some time ago, but they've chosen to launch last month for commercial reasons. But in particular, I feel like we need to move to a world where we can validate systems much more efficiently without requiring a 1,000-car fleet to test for a whole year. How can we have the data offline to be able to do the tests and simulation and through offline evaluation such that with a new idea, we can validate it, let's say overnight, and ship an over-the-air update to our fleet? I think that's the world we need to get to, where validation of a system doesn't cost billions of dollars in multiple years with a gigantic fleet, but how can we do it more efficiently overnight? And that can drive the innovation and the kind of over-the-air updates we've seen and to push forward software and other less safety critical realms.
Can I ask you more about your path to commercialization from here? Sort of what does that look like?
I'm really excited to see this technology scale. And right now we're very much focused on the technology narrative externally and internally exploring a number of different use cases. But I think it's important to keep the narrative focused on the technology, just because I feel like getting undue hype around this sector that's already been overhyped is very damaging. Having said that, personally, and as Wayve, we're very excited about mobility across public transport, ride hailing, and delivery. I think those are the areas that is the future of transport. And we see our product as a learning system and data. And given those two, we can deploy very efficiently into a given mobility vertical. We want to be able to adapt very quickly, like I said at the start of this conversation, to new things. So to give a more concrete example, I think it's really only us and Tesla that are really investing in a computer vision driven, scalable approach that doesn't require an HD map. And I feel like there might be a world where we see Tesla act as more of a iPhone, if we're to use a smartphone analogy, where it's fully integrated. And what we might build is something more like an Android, where we can work with different OEMs, like Android is done with Huawei, LG, Samsung, etc. And we can build a system that can integrate with many different types of vehicles, address many different use cases. We don't want to commit to a single platform like perhaps a company like Neuro has done with their R1 bot. But we want to be able to address different customers' needs, because we see each marketplace and each customer are very knowledgeable in the way that mobility and in particular autonomy will need to be applied to their customer's use case. And we want to be able to have the learning system that can adapt to that need. I think that's a particular reason why it's important for commercial fleets and for customers to engage with autonomy early. I've seen many of the less educated fleets think about autonomy in a way that they want to wait for a winner and then choose the winner to apply to their fleet. The reason why I don't think that'll work is because of the operational expertise and experience that's needed for that particular use case to be able to develop autonomy. So we're very excited about going out and working with different OEM platforms, with different marketplaces and fleets to be able to really scale autonomy to the world.
And that seems kind of like a challenging problem to make a system that, can adapt that way. So I guess, how do you think of making it adaptable to, each different vehicle of different sizes and shapes?
Yeah, that's why we talk about this a lot internally. We haven't made any design decisions that preclude us from scaling to 100 cities and 100 fleets. That's very much the focus of what we are building, whether it's things like over-reliance on internal calibration of sensors. If you do that, then you can't adapt to different sensing locations, or whether it's over-reliance on virtual or physical infrastructure. Rather than adding a different sensor for every edge case, we want to improve the intelligence on board our platform. I think if you think about some of the stats around what humans can do with our two eyes, we have about 10 gigabits per second of information come from our eyes through to our brain of information. It's a very lean sensor compared to what we might see from a camera. Let's say even something as low as a 1 megapixel camera that we're seeing on some today's OEMs, ADAS or L2 driving systems. And so I think it's really about focusing on building the intelligence behind these sensors and being able to focus on systems that have a feedback loop that lets you grow with complexity of data. That's the key to being able to scale. And that's something that we won't compromise on.
By sticking in the visual sensor domain, it seems like it does give you the opportunity to either install the hardware on a bunch of different other external parties' vehicles, or even accept data from external parties coming off of their systems. I mean, is that a potential partnership route for you that you see in terms of solving the data problem? Is like that the solution to that, essentially?
Spot on. That's exactly what we've done. I think if you think about the traditional approach to self-driving that requires lots of rule-based tuning, you need your own fleet of autonomous vehicles that cost more than $300,000 per vehicle, per robot. And this is just hugely expensive to be able to tune your rule-based system. With machine learning, we really need tons of off-policy data, where we just need arbitrary driving data to be able to learn our representations and learn with our deep learning models. Coupled with the fact that our sensing platform is very scalable, we're able to put sensing platforms, let's call them full self-driving ready sensing platforms, on commercial fleets at scale to build up that data asset that lets them commercialize autonomy, that lets them build the safety case while we work on piloting an autonomy use case with them. So we absolutely see data as being valuable, and building up that data asset is something that we're very good at.
How sensitive are you to onboard compute? Like, I imagine you're not putting whatever the fully spec chip would be in those systems, maybe because you don't even know what it's going to be. But how do you think about the onboard compute problem? And can you just use off the shelf? Does it require designing your own ASICs? What does that look like?
Yeah, for the data collection platform we've built, which is essentially putting 6 monocular cameras, which is what we use for our sensing, around a vehicle to give them surround vision, that can be a very efficient compute node. Essentially just needs to be able to compress that data and pipe it through 4G to the cloud so we can aggregate it for learning. Maybe some small local amounts of parallel compute to do machine learning to be able to detect the right data to send back if we're not sending back all of it. That's very true with the large fleets where, well, as we scale that data, it's just too much to take all of it. But that can be very lean. But as for the self-driving, the difference is you need a bit more parallel compute to be able to run our models. You need the redundancy and backup computer required for autonomy moving towards real-time embedded compute and the like to build the safety case. That's all very important. But the key thing to emphasize is that we're not talking about a 2 kilowatt system that some of our competitors use. Our current system on our dev fleet is about 230, 240 watts. And I think we can get that down by an order of magnitude as we productionize. The key thing is that we invest in compute at the training side, but the deployment compute is very lean, very efficient. That's the beauty of deep learning.
People talk about not just the power envelope, but even the kind of the latency of running through a cycle with the compute. Do you see that as either a constraint that maybe it exists today, but just by dint of Moore's law or, improving compute, it won't be an issue? Or do you think that's a potential constraint as well?
Look, I don't think so. When you have complex connected vehicle approaches to AV, I think all these latencies really matter. But when you're just literally, for those that have played around with deep learning, literally our onboard compute, when we drive our self-driving car, is literally running model.forward. It's doing a single forward pass of a neural network with all of the synchronized input data. It's a very basic inference system. And I don't think latency is a huge problem, especially as we're focusing on urban driving. Maybe it becomes more of an issue at highway speeds, but we can easily run a model at 30 hertz, which is more than enough for urban driving. I think looking at some safety calculations, even 15 hertz might be sufficient at a very basic level at low speeds, but that's not a front of mind concern for our technology.
And as you think about how you'll potentially prove to regulators, hey, my system's safe, it's safer than humans, there's been research that's said that it's a certain number of miles. We've estimated it's like between 1 and 10 billion miles that you need to show. Do you consider that on a scenario by scenario basis? How do you think of that?
Yeah, we do. We see that we need to build up the evidence-driven safety case on a scenario level within the operational design domain, within the ODD, the driving domain that we're deploying in. Now, this might come from a variety of sources. It might come from on-road testing. It might come from looking at log data or off-policy evaluation that we've got, or it might come from simulation. There are many different sources. It could even come from shadow mode from units we've deployed that aren't capable of actually driving. There are a number of different ways that we can validate this, but we must generate the statistical evidence on the scenario basis to be able to deploy. Absolutely.
Have you found that, do you think that regulation is something that could potentially hold you back? I guess, how do you think of regulation around the world? And then what markets do you find sort of the most interesting opportunities for Wayve?
Yeah, we've been really impressed with how regulation is handled in the UK. It has absolutely enabled everything we've wanted to do today. We can test on any road throughout the UK, and we are testing throughout the UK. We recently trained a system in London, deployed it in places like Cambridge and Birmingham, and showed that it could drive with similar performance metrics. It's great to see that it's very technology agnostic. It's not overly focused on regulating for, let's say, a HD map or a rule-based approach, but it's technology agnostic. It's supporting what we're doing, which is one of the key concerns we have, given the large stakeholders are firmly in the traditional historical approach of doing autonomous driving. So that's great to see. And I also am not super concerned about this going forward because, look, the incentive for autonomy is so large for a country's both GDP and also for reducing road deaths. And so if a country actively regulates against self-driving, I think they're going to be at such a competitive disadvantage that there's a very strong incentive for that not to happen. So I'm not hugely concerned about it. I think some of the most progressive regulators, and maybe that's because of the maturity of the technology deployed is in some of the states in the US where we're actually seeing testing without any safety driver on board. That's great to see. I don't think the UK is far behind, and it's something that we've been happy with the dialogue we've had with them to date.
And you said that public transit was something that you'd tackle along with logistics and ride-hailing opportunities. I guess why public transit? Because when we've thought about what we think will drive the adoption, we've always thought it could be this big cost differential that you get with autonomous driving. And it seems like that would be a smaller differential in that case. So I guess what makes it an interesting market?
Yeah, I think the biggest market to exploit is clearly ride hailing. And certainly that's the biggest prize. It's interesting to reflect on the technical complexities between these applications. I don't think it's actually that much different between ride hailing and delivery, for example. Public transport can have its other complexities, but the fixed route nature does make it a little bit more simple, if you could say that. But We really care about speed to scaling this and getting access to data and moving quickly. And I think working with commercial partners in ride hailing and delivery spaces is going to make more sense short term. But if you think about the future of mobility and what we really want to support in terms of we work with electric vehicles, we are very focused on building a sustainable future. I think we're going to see mobility in urban areas that it has to be multimodal. It has to rely on public transport, micro-mobility, walking and biking, as well as low occupancy ride hailing, let's say. So figuring out how a technology can really enable that is going to be very important. But I absolutely see a key requirement for there to be public transport for sustainable mobility in cities in the future. And I think we can contribute there, certainly on a safety and efficiency level.
In some of the partnership discussions, I imagine discussions of like who gets the data and how they get to deploy it becomes a little bit fraught. The industry has some history of good ideas that require different entities to agree how to share data, just not actually really getting to market in a way that seemed to work. Can you talk about some of those conflicts and how you can resolve those, or how you position yourselves to basically advance your technology while helping your partners advance their interests as well?
You're right. That's been one of the most important points to get right in the partnership conversations we've had to date. I think everyone, well, at least those that have looked into the space, realize the intrinsic value in data and building up a data asset, certainly to not only enable the autonomy for that platform, but then also to enable the safety case. It can be hugely valuable. Where we position is that we're very focused on building a scalable autonomous driving system. So we work with partners where we solely focus on using the data internally for advancing self-driving. But we work with them to also build up their own internal data asset, to give them the rights, the ownership, and the access of this data, to give them the optionality to go into and exploit learning-based autonomous driving systems. So I think this has been great to see that fleets do realize the importance of this and are willing to invest in it. Certainly the more technologically advanced fleets that we've spoken with, it's been recognized as of huge value. And I think it's something that I've been surprised talking to how much of a difficulty this is for most OEMs, potentially with the exception of Tesla, is that many OEMs we speak to actually haven't been able to operationalize large fleets or build up data internally. They might service many externally that do this, but their own internal belief of data and their willingness to buy data is actually much greater than their ability to collect it themselves. We really want to enable that. It's hard to find economic incentives for that today. We're finding some, but really it's got to be driven by the perceived value for autonomy. And that's what we're seeing the more advanced fleets really understand.
Do you think that, like, if you were to divide the world into two chunks, and we'll leave Tesla out and even Waymo out, but divide it into kind of the ride-hailing type platform companies and then the traditional OEM space, what would you say are the odds of one versus the other, I guess, developing their own autonomous systems or aggressively deploying autonomous systems? Is there an intrinsic winner between those two sets of parties? We have our own view, but...
Gosh, that's probably the most challenging question you've asked me today. It's a tough one, isn't it? I think there's going to be a really complex set of partnerships required to bring autonomy to market in the first generation. It's going to need interactions between the OEM to manufacture the robot, the autonomy provider, such as us, to provide the autonomy solution, the operating entity that actually operates the fleet and potentially owns the assets, and then the marketplace that delivers this to consumer. How far different partners go along that value chain, it remains to be seen, and how the value flows throughout it has been fairly well modeled by people like yourselves. But it's really interesting. I also don't think it's very simple to compare or generalize to put OEMs in the same bucket here, because each OEM is just so different. I'll go far as saying I wouldn't make a general statement across OEMs for that. If you think about the difference between, let's say, Tesla or General Motors and Cruise, or someone like Volkswagen or Toyota, the difference in approach is huge. I think we'll see a world where there are bespoke geographic winners in the marketplace sector that will leverage underlying autonomy technology that drives OEM demand for OEMs to manufacture the vehicles. And so I think it will need to be a value chain like that will exist, and the marketplaces have their own expertise and their own customer verticals. I think we'll see experimentation of many different models, and that's one of the reasons why we've focused so much on the technology narrative to date, is to avoid really building up too much of a narrative around the go-to-market strategy, because I think it's important, whoever solves the technology is going to have their pick of all of these doors, and it's important to maintain optionality. But look, internally we're building quite conviction about some routes, and certainly the ones that we want to explore first.
And what other companies do you admire in the space, whether it be maybe competitors or companies that do sort of tangential things, what Wayve does?
One of the things that I'm so thrilled about in the space is that it's such a huge market and such a hard technical problem that I love the fact that we've been able to be so open about our technology and so open about what we do. We interact and publish a lot into the academic community. We talk openly and blog about what we do. And in particular, because I'm more worried about the industry not solving the problem than I am about, someone solving it and just developing a monopoly. I think there's room for many players, but no approach is going to scale like what Wayve is building. It's great. And I very much push the open and collaborative culture to really move fastest here. Having said that, to answer your question, who do I admire? Well, you can't look past Waymo, who have done a lot of the pioneering work at inspiring and demonstrating some early milestones, even putting out such a huge milestone last month of releasing the first public ride-hailing service. That's fantastic. Look, it's just a very small industry. People flow throughout these organizations constantly, and I've got admiration for many friends who work in many places in this industry. I'd also point out Tesla. I feel like what they're doing is also fantastic. Like us, have really taken the leap and to go and build a scalable system that doesn't rely on HD map and looks at computer vision as the dominant sensor. I think we need more people working on this because this is really the way to bring robotics to society.
And what do you think is the timeline for sort of that? I've heard Wayve has said that you'll be the first to launch in 100 cities. When do you expect that to happen?
Let me avoid the traps of being too specific here because, look, there's so many variables and so much uncertainty at play, like we spoke about earlier. What I would say, though, is that I think we're going to see autonomy technology. We're already seeing it prevalent with brute force in some constrained environments. I think we'll continue to see public services out there offered over the next few years that will scale very slowly and very linearly in that fashion. I think our technology will go through a similar process to Waymo of piloting and demonstrating the safety case and showing it in a number of different verticals. But what I would like to see towards the middle of this decade is for our technology to start scaling in the way that we saw Uber take the world by storm with their deployment of ride hailing. And I think that's the beauty of this technology, is that when it works everywhere. And so if you want to try predicting exponential, we're welcome to hypothesize, but that's how I see it growing.
Would you move through like assisted driving domain before getting to full autonomy? Is that a potential pathway for you to commercialize, or do you think that it's kind of like you just need to take the driver out from behind the wheel?
Yeah, I think you need to take the driver out from behind the wheel. There are a number of well-spoken about problems of over-reliance on level 2 technology. Having said that, it's very interesting to see the full self-driving system that Tesla has released. And there's going to be so much great learning and data that comes from that deployment. It's going to be interesting to see what the consumer reaction is, what the regulation reaction is as that matures and scales. We're fully focused on the vision of full autonomy. I think that's where we've got to remain focused, and that's what will get scaled.
Because even I think it's Aurora that does if you imagine, we have two hemispheres in our brain, I think for an evolutionary reason, but I think it's kind of like they both do kind of different things, but if one gets impaired, you could still survive long enough to procreate, right? So you can imagine if you have a self-driving system that is kind of driving, but the human is kind of driving, and they're kind of balancing responsibilities in some way. And over time, you're bleeding over responsibility into the full self-driving system. That is a potential pathway by which you're getting a bunch of data, but it's not, at least at this point, like a path to market that you envision for you.
On the biological front, I think there's an interesting analogy because there's actually a sea creature that, this is really evidence of why brains and intelligence is exclusively there for movement. The sea creature floats around and eats stuff and develops as an organism. And then when it finally attaches itself and barnacles itself on a surface to live for the rest of its life, the first thing it does is digest its brain because it no longer needs to move, and it eats that protein. Intelligence is purely there for movement, and that's what's so exciting about robotics. I'm getting a bit off topic here, but I think the coolest thing about self-driving for me is that it's the first time we're giving society the ability to interact with robots through a physical interface. If you think about software controlling our lives, hardware has not yet done that, and we're going to start to see cars drive down the road and a human will be beside it, and they won't consent to a robot being beside them, but it will be there helping them, adding value to society. And we haven't seen that before. Domestic robotics or factory robotics don't count because they're behind closed doors. This is really the first example of that. I should probably get back to your question. Look, if it's on mission, then sure, but it has to be on mission about providing more data, providing an economic path to getting our hardware out there, to getting our sensing and our data collection out there towards full autonomy. If it's on mission, sure, but it's got to be motivated by accelerating our data and our validation towards full autonomy.
How big is your team now? if that's on the record, or if you care to divulge.
We're 70 people. Our headquarters warehouse is in King's Cross, right in the heart of London. The streets we most commonly test on are some of the busiest streets. They, full of really complex roundabouts, multi-lane, multi-agent interactions. They're the most fascinating machine learning problem to tackle. The data we get is so fascinating from there. But yeah, we operate a fleet and a team out of central London.
Have you looked at the kind of neighborhood electric vehicle space at all? Is that a potential area, or even micromobility generally? Are those potential data collecting assets for you, or no?
Potentially. I think if you think about scooters and bikes, it's a bit harder to get the kind of package you need on them to be able to collect data, sensors, and the compute and the power requirements. I mean, it's not as bad as when I used to work on drones when you were really weight and power constrained, but it's a possibility. I think there's so many things out there that could collect data for us. We may as well focus on vehicles that are most natural. But like I said before, we need to absolutely interface with micromobility solutions because that is a key part of the future of mobility, I think.
One of our theories on what the OEMs basically have the manufacturers to respond to Tesla, since they've been, or many of them we think are basically painted into a corner on high performance electric drivetrains. And so we think there's the potential for them to move into neighborhood electric vehicles where it's more kind of golf cart like. As you introduce autonomous, like you're going to need different form factors. You're going to need things that just go around town. And then if they pivoted in that direction, they could just heavily sensor the vehicles and hope that, they can make their margin back in providing some partnered or on their own autonomous opportunity.
And that's what I mean about it being so important to be able to adapt to society's needs as demands change. And, if that vehicle becomes dominant, our system should be able to adapt to it very quickly. We actually started with working on a Renault Twizy, which is a small two-seater electric vehicle. That was the first vehicle we prototyped when we started in Cambridge, working in a garage. We had Ethernet cables going out the window, coding away all day and night, driving that little electric buggy around the block. It was fantastic. The Jaguar I-Pace that we work on today is a little bit of a better office to sit in with a more luxurious interior. But yeah, and look, I'm hugely excited to read that the UK government has also banned the sale of new combustion engine vehicles from 2030. So I think we're going to just see more electric vehicle infrastructure proliferate throughout the UK, and that'll happen globally as well, I'm sure.
Alex, it was a pleasure talking to you. Thank you so much for coming on FYI, and we wish Wayve all the best and hope to see your autonomous solutions everywhere in the somewhat near future.
Thanks so much, Brett and Tasha, and hopefully we're all riding the wave soon.
Indeed. All right. Later.
ARC believes that the information presented is accurate and was obtained from sources that ARC believes to be reliable. However, ARC does not guarantee the accuracy or completeness of any information, and such information may be subject to change without notice from ARC. Historical results are not indications of future results. Certain of the statements contained in this podcast may be statements of future expectations and other forward-looking statements that are based on ARC's current views and assumptions, and involve known and unknown risks and uncertainties that could cause actual results, performance, or events to differ materially from those expressed or implied in such statements.